at the record button. Got the Zoomers in front of you, got this over here. Zoomers, can you see, hear everything okay? We're good? All right, do you want to sit down or stand up?
I will probably stand.
Okay. Do you want to see yourself or not see yourself?
I want to see myself so that I know if I walk out of
The show.
you
Yep,
know, like
got it. Yep. I have trained myself to sit down and stay put, but there you go. Now you can make yourself
I don't have that training.
wander around.
Yeah.
Okay, carry on.
All right, so let's go
And the
back up here.
glasses.
So y'all did a good job once again. Everybody's right here. So with a numeric variable that's predicting another numeric variable, either Pearson correlation or a general linear model, we'll capture that relationship and it'll be the same. This one is a little bit more interesting. Folks are split 50-50 in both classes, online and in person. So that's interesting. So for one binary variable, predicting a numeric variable, you can use either. Anybody want to explain why? And I'm trying to watch the chat, so please feel free to jump in there too.
You said you had a theory, right?
I do have a theory. I want to know if other folks have a theory or not. But maybe let's come back to this. This one might make sense after we look at the other one, which y'all got right. So for one nominal variable predicting a numeric outcome, it has to be a general linear model. So why is that the case for a nominal variable? Maybe we'll start at the beginning. Nominal variable. How do we... Categories, yeah. And since it's categories, what does that mean for us in terms of how we set up our model and how we code things? Can we just put like 1, 2, 3, 4, throw it in the model and call it a day? No. Heads are nodding no. Why not? And what do we need to do instead? Any guesses? Anybody want to take a stab at it? I promise I won't. Oh, distance between each variable is not the same. That is true because they're categorical. So there isn't a distance between the variable categories, right? There's not a distance between Catholic, Muslim, evangelical, right? Like those are just categories. So then what do we have to do if we had a nominal variable like religion trying to predict something? Yeah, you compare groups to one thing, right? So we would set it up with some sort of like indicator coding or something like that, which would mean that in order to capture this nominal variable, it's not one variable, we have multiple things, and so we have to take those as like a chunk. And in order to do that, we need like a linear model. We need to consider them as a chunk or we're not capturing the whole thing. Does that make sense? Okay. So if we go back up here to the binary variable, the definition of binary is it's either on or off, right? 1 or 0. So it's literally one variable, just like with having one numeric variable. So we can look at the on or off connections between it, and that's why we can use either person correlation or the general linear model, because it's one variable connecting to another variable, just one-to-one. So my theory was that people maybe got a little mixed up in terms of like, because binary is a weird case of categorical, kind of, right? It's kind of categorical, but numerically also kind of not, because there is a difference between 1 and 0, but it's not exactly the same.
That's the only thing you can do.
Right, yeah. So,
Yeah, I think I was in the wrong category, and I think the way that I was thinking about it is like, how do you put it into words, like a Pearson correlation? And so when I think about correlation, it's like as years of education increases, so does expected outcome, or like so does how much you make, right? And so with a binary, it doesn't necessarily always make sense to say, like, to explain it that way.
yeah.
Like, I get why it can be either, because it's just that one jump, but like trying, like our marriage example, trying to say like as marriage increases, so does like
Yeah. Well, and I think when I think about it, I just think of like being married
yeah.
means that like it's this bigger relationship. So, kind of, I don't know if it's technically correct, but I think about it like in terms of likelihoods, kind of, right? Like being married means that like you've got a greater chance of this other thing going up on average most of the time, right? Okay. So for the question on Zoom, did that discussion help with that or no? Yeah? Okay. Cool. Yeah, you had the same question.
Can
So
we add another one to this list?
okay, bonus question from Lisa. Here we
Yeah.
go.
There's a third way to answer this question of whether there's a
I'm gonna-
relationship between a binary variable and a numeric one. It's not on the page.
Oh, third way to describe the relationship between a binary variable and a numeric
It is the
variable.
same thing, just with different words.
What's the other word that you can use for that?
Requires gestures.
Gestures, if that's helpful. I don't know if it is for me. I think I'm stumped.
I'm just trying to keep myself awake.
Okay, no, go for it. If you think you've got the answer, I saw somebody's hand go up. And if that was an accident, sorry to call you out. Okay. Yeah.
I'm thinking of independent samples t-test.
Independent samples t-test
Because
is what
the
Lisa's thinking
t-test
of.
statistic you would get from that is the t for the slope in a model, or the t for the correlation.
What is your gesture for that?
Gesture is t.
Big
or big T.
T. Big T.
There we
That
go.
also means like timeout.
Yeah.
Or technical.
F ratio work as well? Or
If you want to take your t and square it and turn it into an f, absolutely. Yep,
Okay.
same information. Yeah, if you did an ANOVA on one binary variable with two groups, that f is t squared. Same deal. Yep. It's a semantic distinction.
The more you know.
The more
That's
you
what
know.
we're here for. All right. So then let's see. Okay, almost everyone got the ordinal. Okay. So next question. Okay, if we have an ordinal variable with 4 categories predicting a numeric variable, when is it okay to treat the ordinal variable like it's numeric? Only if they are, like if the difference is the same between the different categories, which you all pretty much got. Are there any questions about that just while? Okay. All right, now imagine you're predicting a numeric outcome from a nominal predictor with 5 groups and indicator coding. And when you do this, the p-values for the 4 individual predictor slopes are not significant, but the Model F test is. And so this is one of those questions where you had to get the incorrect conclusion. Which of these would be wrong? So, folks answered it really well. Basically, the difference between the reference group and the alternative groups are not different. That's why there's no significance there. But the F model statistic can be significant. Model F statistic, switching my words up, can be, because there could be a relationship between those slopes. There could be differences in the alternative slopes from each other as opposed to from the reference group. But when we have a nominal variable, we're always comparing back to that reference group, however we have set that up. And probably that's going to be driven by some sort of theory or something like that. Okay. Again, this one is looking good. If you add another variable to your model, probably you're going to see a slight change in the first one. So if you start with A predicting C and you add in B, the slope for A may change because B and A may have like an overlap or something like that. So it won't be the same likely across all the models. Okay, so this one. In the same scenario, so where you have A predicting C and then a separate model where you add in B, which of the following will also be true? This one was a little bit more all over the place, but basically you're adding one variable to the model. And so if that slope is significant, you don't need to do a whole F test because that's just the way it works. But if you were to add D to the model, then you do have to, because otherwise you're not able to capture and like figure out what the individual contributions of changes are. Any questions on that? Alrighty. Okay, this was another one that wasn't quite perfect, and that's okay. So, semi-partial is like the unique contribution overall. Like this is the amount of the pie that it takes up. If you're looking at the whole pie altogether, this is what A explains. But some folks chose this one over here instead, and this is the one for the partial. So the good news is that you were getting the right definitions. You had the same concepts in mind, you just switched the labeling for it. So just make sure that that distinction between partial and semi-partial, that's going to be a point for you to review. And then the partial is the amount that it explains that's left over of what hasn't already been explained. So it's way less intuitive than
The leftover pie.
yeah, half of the leftover pie. That's what Lisa says. So, yeah. But again, you're on the right page. You know that there's a distinction between these things. So, just an area for review. And then, lastly, all else being equal, which of the following is not a consequence of increasing sample size? So, if we increase our sample size, we end up with smaller standard errors because we divide by a square root of n, right? And so if your n's bigger, your denominator is going to be bigger, and you're going to end up with something smaller. If you end up with smaller standard errors, you can end up with smaller p-values because you're looking at a much narrower distribution. And so, yeah. And then you end up with greater statistical power. But there's nothing we can do about the effect sizes. Those are what we go out and look for in the nature of our data. So if you manipulate that, that's just straight up cheating and academic dishonesty and making up data, and that will get you fired. So don't do that. But yeah, the effect size, it's going to be whatever it is within your data. Any questions on that or any of these topics so far? Again, y'all did a good job, so.
And you get 3 points no matter what.
Yeah, and it doesn't matter how you did because you get your points.
Grades were updated this morning.
Excellent. Cool. All right. And that's it for me. Back to your regular programming with Lisa.
That's me. Alrighty. So yes, I think that went pretty well on the whole. Now I gotta remove my head because I don't want to look at myself while I talk. No, it's.
you're going to stay in one place.
I do. I sit myself down so that I cannot move very far. Plus that I'm tall enough to see everybody, which is nice. So not used to that. So anything else that you wanted to go over with respect to this? Feels like folks are getting the hang of things, or at least we're able to with after consulting your notes, which is fine. Good. All right. Then what we have on our agenda next is homework 4 is due on Monday, and the rest of example 4B is designed to help you complete it. So whenever you are in a situation in which you are addressing research questions about unique effects, meaning what does variable A predict above and beyond variable B, those kinds of questions, you will have to make a decision as to whether you want to examine all of the effects at the same time and control for everything sort of simultaneously, or whether you want to go with more of a layered approach where you're adding in some things first, talking about those, and then seeing the contribution of new things, talking about those, and so on. The latter is far more common, and that's why homework 4 is set up that way. So unlike previous homeworks in which the instructions were, put this in the model, now take this out and put in this other thing, you're going to be adding something, talking about it, or choosing answers about it, I should say, adding something else, choosing answers, adding something else, choosing answers, and sort of a building process. So I wanted to give you some code that would help make that a little bit more straightforward, but then I also wanted to show you how you would approach the same questions from a simultaneous analysis where you didn't do a layering system. So relative balance of folks here, I'm going to go through both Stata and R for this since there is a homework about it, and I want to make sure folks understand how to use these commands. So I am on page, not on page 1, 8, thank you very much, of example 4B. Do you remember the story from these predictors? Should we go back over that briefly? I should assume you don't have perfect recall from Thursday, per usual. Yeah. So these are made-up data to look like real data. These are fictitious older adults in a study examining performance in a measure of crystallized intelligence. We're calling that cognition here for short. And I have a fixed intercept as well as a linear slope of age. So note the subscripts on here. Why does age have an I? What does that tell your reader? Don't overthink it. It changes. It's a variable, right? In contrast, beta 1 doesn't have an I. That's a constant. So that means that if beta 1 is 2, it's 2 for everybody. Age is the variable that is in your data that changes across rows. And what does 85 convey? Yeah, centered at 85. So I like to put these in my equations because people who understand equations are going to read this and go, oh, that's my reference person. If it's buried in the text, sometimes it gets trickier to try and keep track of what each variable means. So I have a linear effective age And on Thursday, we had examined a potential quadratic effect for a bendy line instead. It didn't help, so I'm going to say, okay, going to leave it as is. Did the same thing for grip strength, which is supposed to be a proxy for physical function. So this is scored in pounds per square inch, where 9 pounds was near the average of the data set, so we have a linear slope for that. Likewise, we have a binary variable for biological sex, where men are the 0, women are the 1. So up to this point, I would say that we have 3 different conceptual predictors in the model at the same time, in terms of age, grip, and gender, and each of these takes only one slope to talk about it. When we get to this line, though, that is no longer the case. So these 2 slopes are meant to pull apart the 3 dementia diagnosis groups, where there's none, never going to be diagnosed, there's future, is on their way there, but they're not there yet, and current, meaning they already have a diagnosis at this point in the fictitious study. So dementia group to me is one idea. Like dementia status is the construct, but it takes 2 slopes because I have 3 groups. And the 2 slopes for 3 groups rule is a constant. So long as you have 3 groups, one of those groups needs to be covered by the intercept, and then 2 slopes are going to pull the other groups off of it somehow. Somehow is the key word in that sentence, because there's different coding schemes that get you different results. So for something like this, I went with what's known as indicator coding, which is the standard approach, where none is the group that I designated as the reference. So beta 4 is going to tell me how the future group differs from none. Beta 5 is going to tell me how the current group differs from none. That means I'm missing one. I'm missing F versus C. So it could be the case that I add these 2 slopes to the model and neither of them is significant, yet the contribution of the 2 is significant, because the particular slopes you get back from these sorts of binary coding schemes are only some of the possibilities. So if there's 3 groups, there's 3 differences. If there's 4 groups, there's 6 differences. If there's 5 groups, there's 10 differences, and so on. So the ones you happen to get are only part of what's possible. And that's why testing the contribution of the slopes that delineate groups as a set is necessary, because then you're asking the question, does group matter? And then from there you can say, how does it matter? Like, which groups are different from each other? What is the story behind the omnibus, that's the word you'll hear, or overall effective group? So these 2 things I can't really interpret separately if I want to talk about how group contributes to the model. I got to find a way to collect them back together again. So that's my story. And then E, what's E again in notation? Yeah, residual or error. This is the idea that the model is wrong. How far wrong is it? E is what's left after you build a predicted cognition outcome from all of this stuff. So ideally, as we add predictors, each E for each person, the set of E's collectively gets smaller. And we keep track of their variance so that we can examine how much of it is remaining. All right, so Stata folks, you're going to love this. The vast majority of your homework can be done by 1 line of code. Has anyone tried this yet? No, you're smiling. She's like, I can't wait. It's going to be fun. Okay, so Hillary did not know this was a thing either. I learned about this fairly recently. So there is a command in Stata called nestreg that allows you to run layered models of many kinds. I believe it works with mixed and like generalized models and all the other kinds too. So it's not just for this. But the idea is that for this we're using regress. The first word after that is the outcome. And then what goes in parentheses is what you want added at each step of the analysis. So this 1 line of code is going to generate 4 models, 1 for each set of parentheses.
So the order matters.
The order does matter. Yes, it does. And that's the problem, right? Because like I can give you a reason why I think this is the order that these things should be examined in, and reviewer 3 can come back and say, nuh-uh, and they're like, you have to defend it. The reality is that when I put age into the model at the first step, it has the best chance of explaining variance because there's no competition. Whereas if reviewer 3 is like, nuh-uh, I think age goes last, and it should go like that. Well, now when I enter age, it's going to have a stronger effect in order to still make a contribution above and beyond all this stuff. So it could look like it's a bigger deal if it's entered sooner than something that's entered later and already has a bunch of stuff working against it. So I will show you the sequential approach because you will see it a lot, but just understand that the sequence is debatable. And I think it's a safer thing to do to not have a sequence if it's debatable and just to extract the information you need from one model. So we'll do both. But yes, order matters, and this is 4 models all at the same time. And I am going to store the results of these models so that I can access them to compute effect sizes in Stata as well. So block 1 is what it's labeling this as, is age 85. And this is an example of when the test of that age slope is telling you the same thing as the test of the model, because there's one slope in the model. So t squared minus 4 down here is the 16 for the F. Same thing. So age has a linear relationship. This is giving us the same information that a Pearson correlation would have given us at this stage. So age by itself is responsible for about 3% of the variance in cognition so far. Fine. And if we go down to adding grip strength, the coefficient for age used to be minus 0.54 when it was by itself. Note that when we add grip strength, it is weaker, so less negative as a pattern, minus 5.4 to minus 4.2. So the effect of age is smaller after controlling for grip strength, which is not unreasonable considering we would expect age and grip strength to have something in common. So after controlling for age, I would say for every pound you can squeeze on the little test thingy, your cognition is higher by 0.8. For every year older you are after controlling for your grip strength, cognition is lower by 0.4. So if you're talking about the effect of a slope, you can say higher or lower in terms of what it does to the predicted outcome, as we have been doing. Adding in gender in this case further adjusts the previous results because they're likely correlated with gender. And if I'm in the one group, I am lower. So the coefficient always applies to the one group when you have a binary variable as a predictor like this. And then last but not least, we add in dementia group status. And dementia is bad for you, as you might expect. If you are going to get dementia, you have a lower predicted outcome by 5.7 relative to people who are not ever going to. If you already have it, relative to people who are not ever going to, you are lower by 16. And what about the difference between future and current? That's going to be like 11-ish, minus 5 versus minus 16. We have to find that as a linear combination still if we want to be able to talk about that. So this is handy just to have one line of code run multiple models, but what's even handier is this happy little table it provides. So this is telling you at each step what the F test is for the change in the model relative to the previous step. So in step 1, it's relative to an empty model, adding one slope of age. So the F for that one slope is given here. The R square for that one slope is given here. Block 2 then is adding in grip strength and keeping track of the overall model R square and the change. So this is another instance, just like adding in gender, these two middle layers here. These are examples of situations in which this table with respect to the F test is unnecessary. If the one new slope you added is significant, then the change in the R square that it created is significant. It's the same thing. So the reason to do this really is just to get these numbers right here, because then you don't have to actually get your calculator out and compute the change. Calculators are bad. Okay, not as bad as dementia, but bad. Because calculators don't replicate. And they don't provide an easy record of what you did and why. That's the issue. So up to this point, we've added 3% for age. After controlling for age, we picked up about 4.5% more After controlling for age and grip, we picked up about 2% from gender. And then the big one down here, a change in the R-square of about 18, 0.18, up to 0.27. So this is really the only new piece of information, because this is a 2 degree of freedom test, meaning lumping the two dementia slopes together, what is the overall impact of group? The two slopes that we have are only 2 of the 3 possibilities. So this would be needed to say which slope it is, and to also take into account their joint contribution if these two predictors are correlated. Okay, how are we doing? So not bad on this one. Any questions on how nest egg works or how you should use it? Okay. Moving forward then, I wanted to show you some other examples of how to get effect sizes for situations in which you want groupings that are not dictated by your layers. So in Stata, I'm accessing saved results to do various computations here. I'm saving the sums of squares residual and the sums of squares model so that I can compute not pseudo R-squares, that's the other class, semi-partial R-squares and partial R-squares. Yes, this is hard to keep it straight. So I'm saving these things to do math on down here. So everywhere that you see these dollar signs with the teal, what's happening is it's accessing the number that was in the results that I saved that number and I gave it a name. And then when you want to refer to that number in the saved results, you put a dollar sign in front of it. So like this is saying, hey, save it as SS full. And this is saying, now go use that and stick that number in here. And if one way you can remind yourself is that if you learn computer programming like this, someone will pay you. So dollar signs for the win. Just a little bit of programming can make your life a lot easier. So I am running a reduced model to show you an example of how I could see what the contribution of age and sex is together, because they were entered in separate steps up above. So I'm computing the difference in the sums of squares for the model relative to what I get when I kick those two terms out as compared to the full. And then I can throw those into these formulas that compute partial R-square or semi-partial R-square. So those values end up being right here. So it looks like in terms of the contribution to the R-square, age and sex do 0.036 of that. Not of, but that's the amount. And the two slopes together are significant. So test is a way in Stata, it works across many different types of models, where you can lump slopes together and ask it jointly if they're different than 0. And it doesn't have to be two grouping variables or anything in particular. It can be whatever you'd like. So this is just an example of how to make a custom hypothesis test. Looks like the two contribute, and here are the corresponding effect sizes for that. And then last but not least, for terms that are directly in the model and you just want effect sizes, there is a command in Stata called pcore. So if you list the same predictors that are currently in your model, it will compute partial and semi-partial correlations and their squared versions with the outcome. So you can get a lot of stuff by default without having to do much work. Last but not least, Cohen's d for things is something that I couldn't find built into Stata anywhere. So I did that by accessing saved results. So this little formula right here, you can steal and repurpose for any model. It will work because it's pointing to the spots where the numbers are, not the numbers themselves. So this is 2 times t divided by the square root of denominator degrees of freedom. So I'm getting the effect of gender so that I can get the effect size for that, as well as the group differences for each dementia category. So a d of minus 0.35, for instance, means these two groups are different by about 1/3 of a standard deviation. So I'm doing that for all the things, and then the linear combination last up. So lots of code to get different things. I don't want to get too far into the weeds to this, but I did want to give you examples for your lives, right? If you're like, how do I do this in Stata? Hopefully you have enough to go on here that you can start to figure things out. They also have a lot of really good documentation, and I found several YouTube videos of other faculty who teach Stata that have been very helpful for me to learn how to do things. So I just want to give you some resources for the future, but I don't expect all of this to make complete sense the first time you see it. That's what I'm saying. The same process we're going to go through in R in just a second. But questions on any of that? Okay. R, folks, you got to do a little more work, but not too much because I wrote you functions. So in this case, I had to write separate models to do the layers. I could not figure out an analog to nestreg. Doesn't mean there isn't one, just means I couldn't figure it out. So I have age by itself, adding in grip strength, adding in gender, adding in dementia group, and then we end up at the same place in terms of the output. Now, to be able to get effect sizes from the joint model for all of these things, I have to run these separate little functions. So what this does is compare two models for you. I built this function. It uses other functions inside. So the arguments to this function called r squared change f, what it is doing is meant to mimic the same table in Stata where it does all the stuff for you, right? I'm trying to get you this. So I built it. Okay. Here it is. So it wants to know the reduced model and the full model. So for instance, this is the model that has age and grip. This is the model that has age. So I can get the unique contribution of grip. This is age and grip. This is age and grip and gender. So I named these in terms of what they all have. You might just go with model 1, model 2, model 3. Otherwise, you'll have to make sure your names exactly match. But I was going for transparency, not efficiency. So then each of these calls spits out a table like this, where it first reiterates the r square for the overall model. It then gives you the change in going from the full model down to the reduced. So basically, like, how much did the r square go down by taking out this thing? Then it tells you what its unique contribution is. I get the f-test for that unique contribution, which anytime it's 1 degree of freedom, that's redundant. And then I had it spit out partial r square and semi-partial r square. And two of these numbers are the same thing. R square change and semi-partial r square. They are the same thing. How much more variance did the model account for? Either way, that's what it's telling you. And then I did an example for age and gender just to show you what that would look like, but the code is exactly the same. And last but not least, I built a function that takes that model results table and adds Cohen's d and partial r effect sizes to it, so you can get the analog to what Stata does with the pcore command. And last but not least, one model implied difference for the difference among the two non-reference dementia groups and its effect size. And that's it. Ta-da! Like, whoa. We got through the end of it. So this is an example of what the full write-up would look like. Typically, you have a correlation matrix among the variables that are in your analysis. However, we're missing some. What am I missing in terms of my relationships here that's not in my table? I have cognition as my outcome. I have age, grip, and sex, where I have noted that the women are the one. My grouping one. My dementia group is not in here. Why? Did I forget?
Because of what we talked about with the formative assessment, because it's groups.
Because it's
And
groups.
talk about correlation.
Yeah, so dementia group in the data set was stored as 1, 2, 3. None, future, current. That's ordinal at best, but those aren't numbers. So I can't take 1, 2, 3 and add it into this table as a variable and do a correlation with anything. That would make 0 sense. Well, what about my dummy codes? What about the two contrasts? I have dem and F, and I have dem and C. Let's go back up to where those were made originally to answer this question. Here they are. So if I'm talking about the none group, both of my variables are 0. If I'm talking about the future group, the first one turns on to 1. And if I'm talking about the current group, the last one turns on to 1. So could I take these new variables and throw them in my correlation matrix? Because they're binary, right? And we said that was okay earlier.
I would still say no because your zero group, your reference group, lumps in whatever the other group is. So if you're comparing none to future, your none group technically also includes your current dementia patients.
Exactly. So if I look at the first variable here, what I want it to mean, and what it does mean in the model, is future versus none. But if I look at what it means in the data, I'm lumping together none and current against future because it's 0, 1, 0. And the same thing is true for the second one. I want that to indicate the difference between none and current, but what it actually does is lump together none and future against current as the 1. So these binary variables don't mean what they mean in a correlation matrix as what they do in a model. So if you have a way of creating these binary variables that make sense to you and would make sense to have the zeros lumped together in such a way that it still provides a meaningful result, then you could put them in the correlation matrix, but otherwise I wouldn't do it. So what I ended up doing instead, what we went over last week, back to the table, how do I examine a bivariate relationship between a numeric outcome and a nominal variable? You all got this right. It was like question 6 or something. Maybe 4. How do I examine the bivariate, meaning 2 at a time, relationship between a nominal variable and a numeric variable? It's got to be a model. So that's where I had dementia group in its own model, because that examines how group relates to cognition. And the R-square for that model kind of gives me the correlation between group and cognition, but it's giving it to me by using 2 slopes instead of 1. So the R-square for the model of cognition being predicted by group, unsquared, would be the correlation that would be in this table. But it's a roundabout way of getting it there. And usually folks want you to repeat, or at least provide demographic data in terms of descriptive statistics, so you can throw that in the table if you want. I've also seen it to where, like, if you have multiple groups in your model, like you're reporting maybe results from 2 different samples, to save space, people will put the results for one group, like in the upper section of this triangle, and then the results for others in the bottom. So that way you can save space in your manuscript by not having to have 2 tables, because otherwise this is a lot of wasted space for it being blank. So in the narrative, I went through what happened bivariately, what happened in terms of adding the information to the model sequentially, and this is basically me stealing that table from Stata and making it prettier, and then what happened in the combined analysis as well. So then my resulting table would provide estimate, standard error, p-value. I have a Cohen's d for individual effect sizes, a partial r, and a semi-partial r, where I have a note about which ones were combined in that case. So essentially this semi-partial, oh, come back. This one down here, this is for all of these put together. 2 from the model, 1 is a linear combination. And that's it. 14 pages later. All right, how we doing, folks? Can you repeat the question a little louder, please? Mm-hmm. No, you can. So in the example here, let me go back up and find it. Where is the total model? Yeah, so the model combined that has all of the slopes that I want in it, I wrote a function that essentially takes that output, so it would have been like that right here. What it does is takes away the t-values and the confidence intervals, and it adds computed d's and r's. So this is the results of that function. That's essentially my table. What I had to add to it was this last column right here, I added semi-partial R-squares. And the reason that I chose to add them separate is because these are not always valid for individual slopes. So for instance, these are the two slopes for dementia that are in my model. If I were to report a semi-partial R-square for each, they would not really be correct because these share a common reference group. I need to take into account the fact that these are working together. So I had to compute a semi-partial R-square, or the change in R-square, by comparing a model that had these two slopes to one that didn't. And so since that was a separate computation, I built a separate column to keep track of it. But you could easily augment my functions to add that information. It's just then the onus is on you to try to remember when it's valid and when it's not valid. And that's the trickier part. I didn't want to provide results that would potentially be incorrect. Yeah. All right, so this is homework 4. Would you like to know what homework 5 is about? No? He's like, no, I'm not ready for that. It's about interactions. Yeah, it's like, of course it is, because this wasn't hard enough. No, interactions is one of my favorite things. You're like, you have a favorite stat? Yes, I picked this as my job, folks. The enthusiasm is real. I've found a way to embrace my nerdiness and make money off it, quite frankly. This is the kind of stuff that a lot of people don't want to do. And maybe a lot of people is you right now, and I'm okay with that. Someday, what I want you to have are all kinds of tools to put in your toolbox to do the best research humanly possible. That's what I want. But there's a lot of folks in the world who hate statistics. They hate computer programming, and they want nothing to do with any of this. So pragmatically, even if this isn't why you get up in the morning and this isn't super interesting to you, if you can fight your way through it and become capable of using models in your work, like that opens doors for your career that you wouldn't otherwise have. So that's why Hillary's here, right? You're a sociologist, but you are trying to market yourself as someone who can teach regression and undergraduate research methods, right? Mm-hmm. Oh yeah, this is data science. Mm-hmm. Yes, indeed. Yes. It is true. I have seen an increasing number of job ads that say things like, we want someone who fits into our department somehow who will teach the methods classes for us. Like, and so if you can pitch yourself as someone who's capable of that, that opens doors. And just in a practical standpoint, like doing workshops and things, that's how I paid off my student loans, is I taught summer workshops. So you can get opportunities to teach this stuff that can help you as well. But moderation, where I'm going with this, is one of those topics that a lot of people think is really hard, and it's not. I'm going to give you the code to crack this, and then you'll be able to do moderation with the best of them. It's just pattern recognition, and once you see the patterns, it becomes really, really straightforward. But there are lots of workshops in books all about testing moderation, and they make things more complicated than they need to be. So one of my favorite reasons that I like to teach this the most is to demystify the world of interaction terms, and that's where we're going to be headed. Do you want to see just a little bit? Like maybe just like this much, and I promise that I'll pretend that I never said it on Thursday? Okay, fair.